In this video, I am going to explain how to implement hex CPU code. This diagram is a proposed design for the CPU architecture which I am going to use to implement and explain the STL code of the CPU. In the following diagram, the CPU consists of several logic gates such as the ALU, the register, the D register, program counter, and the multiplexer. The first step to implement the code is to derive the API of the CPU. The API specifies the chip name, the input and the output pins, and the function of the CPU. So let's start with an abstraction of this chip. As shown is in this diagram, three inputs are coming into the CPU from different sources in the computer. These inputs are the instruction, enum, and reset. The instruction input is from the instruction memory or the row, which is the value of the selected instruction memory register. This instruction can either be an A instruction or a C instruction. On the other hand, enum is the value of the currently selected data memory register and is the value that the CPU uses to perform its operations. The CPU takes its instructions input from the instruction memory and also takes the value of the selected data memory register as one of its inputs. The reset input is a value that tells whether we bring the CPU back to its initial state or to specific to the start of the operation of the CPU all over again. Furthermore, along with the inputs, CPU has several outputs that are connected to the instruction memory and the data memory. As well, these outputs are called write-m, out-m, address-m, and PC or the program counter. In the CPU architecture, we can see that the ALU gives an output that is written to the data memory. To do so, the value must specify a few things. Firstly, the content that the CPU is going to write into the data memory, which is stored in the out-m. Second, the address of the write operation in the data memory. This is where we want to put the content in the data memory. The output that allows you to write the content to the data memory, write-m. The program counter holds the address of the next instruction, which will then be fetched, decoded, and executed by the CPU in the next cycle. Now that we have identified the inputs and the outputs of the CPU architecture, we can now implement the code of the CPU. This is the HDL code of the CPU that was provided in this task resources. I'll explain this. I'll explain this code to you in more detail by parts as I go along. We have the header section that specifies the CPU interface. It consists of the chip name and the names of its input and output pins. Since we are implementing the CPU chip, the chip name that we are going to write for this code is CPU. As shown in this code, the input pins of the CPU will consist of 16-bit enum, 16-bit instruction, and reset. On the other hand, the upper pins of the CPU will consist of 16-bit out-m, write-m, 15-bit address, and 15-bit PC. This is the first part of the parts, the section in the CPU STL code. We have three different gates: NOT gate, AND gate, and MUX16 gate. These gates allow the CPU to function and perform specific operations. Firstly, there are two types of instructions coming into the CPU from the instruction memory. These instructions are A instruction and C instruction. A instruction has a symbolic syntax of add value, and this value can either be a number that is decimal, non-negative number, or a symbol. If the value of instruction is a number, then the instruction will set the contents of the A register to the specified value in the instruction. If the value of the instruction is a symbol, then the instruction will set the contents of A register to the value that the symbol points to, and this value will not be the actual value in that memory register. On the other hand, C instructions have a symbolic syntax of just is equal to comp and jump. This instruction performs the computation on the CPU which is stored into the destination register or a memory location. It can also tell us that the CPU to jump to another instruction memory address that is pointed by the value or the symbol. In the first line, we can see that the NOT gate is used to tell whether an instruction coming into CPU from the instruction memory is an A instruction. But first, the CPU decodes the 16-bit instruction into an OP code and 15-bit value. If the OP code is 0, then the instruction is an A instruction, whereas if the opcode is 1, the instruction is C instruction. For example, if the instruction coming into the CPU from the instruction memory is an A instruction, the CPU takes the specified 15-bit value and stores the value into the register. However, A register can be fed by either the instruction input or the ALU input. If it is a C instruction, it performs the computation in the ALU and the ALU output is fed to the register. We use the AND gate to determine that the instruction is C instruction. A 16-bit multiplexer is also used to select whether the instruction or the ALU output is stored in the register A. In the next part of the code, we have an OR gate. The load bit in the register would be 1 if either the instruction or the ALU output is fed to A. On the other hand, A register is used to store the value that is fed into the A register. It takes in the input register from the multiplexer and output load A from the OR gate as it inputs. The output A then generates the content or the value that is currently stored inside the register. Next is another mux16 that takes in the output of the register and the value that is currently selected in the data memory register in M. This will select which one to output, A or M. Either A or M will be fed into the ALU depending on the 12-bit instruction value. The AND gate is employed to determine whether the ALU output is loaded to the D register. The D register is then implemented to load and store the value of the D register from the ALU. Next up is the ALU gate. The ALU computes a function on two inputs, which in this case would be the value that is stored in the register and the value of either the A or M register, and then generates outputs. It consists of input control bits such as the ZX, NX, ZY, NY, F, and NO, which are indicators of which function is computed on the two inputs to produce output, whereas the output control bits such as the ZR and G determine the properties of the result. The following code consists of two OR16s, and an AND gate sets the value output to successfully write on the data memory. The first OR16 code line determines the address of the write operations. The second one determines the content of the data memory, and lastly, an AND gate that outputs a value that allows to write the content to the data memory. The program counter is also known as PC is a register. It contains the address of the instruction to be fetched next in this part of the CPU STL code. The load bit of the CPU is determined by the jump bits and all outputs. These lines of code determine jump conditions and checks the ALU output to see if the conditions are met. If the instruction is C instruction and the conditions are met, the program counter is loaded with value that will ask the CPU to jump to the specified value or symbol. The PC is not loaded, the PC is incremented. Incrementing means that the CPU will read the next instruction. And so this is how I understand and will implement the STL code for the hacked CPU. Thank you.